please give a talk.
Okay, actually, thank you very much for the invitation. And I don't want to say nice to be back in Mexico City, but
in a sense, yes.
Yes, exactly. We were just joking, actually, me and my wife, that actually I am zooming myself to Mexico City for an hour or so today. So what I would actually like to talk about is something that I have been discussing with one of my students, Vishwa, which is Toeplitz operator acting on the Fock space. But this is not at all finished work. It is still a work in progress. We have been a little busy lately, so we maybe did a little less than I was hoping, but I think that is okay also to talk a little about things that we are really working on and what our plan is. So what I will talk about, the first part is probably very well known for everyone in the seminar, but I still wanted to mention it, also a few words about quantization, just introducing the Fock space so that we have a common language, Toeplitz operator, few words about group action. I'm trying to keep that in minimum, but I wanted to be able to formulate actually the basic theorem that we obtained with Raoul and Matthew. And I see Matthew is not there, so, but that will, I will keep that as short as I really can. And then I will talk about the main example that is actually done, that is a product of unitary groups acting on the Fock space, and then mention some other examples that we have been looking at, but the work is not really finished. And that is where the Metaplectic group and the Heisenberg group come into the picture. I'm not going really to say much about the Metaplectic group because we are mostly just interested in subgroups. So kind of what was definitely one of my motivation for thinking about Toeplitz operator and quantization, that is because I am also interested in mathematical physics. And there actually this quantization is a very important topic. And the idea is, if we are looking at classical mechanics, we are just looking at a symplectic manifold, say a manifold and then a cotangent bundle. That is a definitive a symplectic manifold. And everything is then described in terms of function. Okay, the position of a object is given by a coordinate function. The momentum is given by the derivative, which is an element in the cotangent bundle. But if we go to quantum mechanics, then we are actually talking about operators. And for example, also now the position actually is the multiplication operator on L2 of L3, or if you are looking at a multiple particle, actually R to the 3n, which is then the tensor product of those L2 spaces, and then you can look at the Fock space, which is then an unbounded number of particles. And the old way of quantization is you take actually equation from classical mechanics and you replace the function by an operator. This does not always work, but there are some actually methods to do it. So the trivial case is where xj, which is the coordinate function, is just a multiplication by the same function. acting on the L2. And there are some rules that one expects actually to hold. As the Planck constant goes to 0, the quantized system is supposed to go to the classical system, but we will not be talking about that. And one can for surely go further, which is much harder, that if you go to quantum field theory and try to connect quantum theory and relativity, but that is not what we will be talking about. But this is one of the motivations actually why operator like Toeplitz operator are important, because that is a very special form of quantization. Okay, so this definitely then actually the quantum theory leads to C-star algebra, von Neumann algebra, acting on a Hilbert space. And what we will be talking about, and that is no surprise, that is the abelian C-star algebras, which are simply actually the function that vanishes on infinity on a locally compact topological space. So I usually do denote this by C sub infinity, also those are the functions that vanish at infinity. And that is just with the usual operation, and if it has a unit, okay, then actually this X space X is compact. And every C-star algebra, commutative C-star algebra, is given that way. And what I somehow think is interesting in this realization is not actually this fact, but exactly how this is actually done. And that is the Gelfand transform. And that is just as you think of the Gelfand transform that goes from the C-star algebra into the space of continuous function on X, which is the space of homomorphism. That is just by applying the homomorphism to A. Typical example is just the error n, actually, where this is really given by the Fourier transform. So the Gelfand transform shows up in many different kinds of situations in harmonic analysis. So in this case, it is not only to realize it as the space of continuous function, it is really also to understand both the space X, the space of continuous homomorphisms, or if you're doing non-abelian representation, and kind of realize this Gelfand transform. Oops. Okay, so this is just what we were just talking about. Okay, the Toeplitz operators say is a very simple form of quantization, and it is done just by, okay, in the simplest way, and I actually have to admit, actually, I started doing it without complex structure. You can do this on other manifolds with a symplectic, have a nice polarization. But in our case, we will only be looking at complex domain with a nice probability measure. And I usually assume that this is given by a density, which is continuous and bounded away from 0 on any compact set, because that really gives that the point evaluation map is continuous. And that is just an application of Cauchy integral theorem.
Yes, so one question. I don't know if it's only me, but I'm only seeing the first page of your presentation. I cannot. You haven't changed the page.
You don't see that. So I see that that can be actually. I don't know what it is with. In my computer, it says that the steering is paused. Okay.
I have the same problem.
Or everyone else?
Yes.
I think it's everyone.
Is it
only The first page.
All of
Is
us
it from
see
your
only
side
just your first page.
Yes, so it says, I think I mentioned that, it says on my computer, sharing is paused. So who actually has power on the sharing? Let me actually try it, stop it, and try it again. Okay.
You're using Mac, and I'm not an expert in Mac.
If that is a...
Oh yeah, it's
Okay.
page 7.
Yes, okay, so now it is working. Okay, so should I go back actually, or?
Yeah, better start from the second page.
Okay.
Oh yeah.
Okay, so this is what I simply did, and I talked about the mechanics and all of that.
Yeah.
And I don't think I need to. Okay, so here is the slide with the continuous function.
Okay, great. Next.
Okay, here is the Gelfand transform.
Yes.
That is the Toeplitz operator. Our Hilbert space will always be the one with the holomorphic function intersection with L2.
Okay.
Okay. And as I mentioned, actually, this is not really necessary to have the holomorphic function. It is really what is necessary is to have a projection. So what we have here, this assumption that you have a positive function, a density function, that gives you that the point evaluation is automatically continuous. And as I said, that is just by looking at the Cauchy integral theorem, so that is easy to prove, and that gives us the reproduction kernel. And the reproduction kernel is the one that gives us the Bergman transform, and that is what we need actually just in general. We need a subspace, a big space, smaller space, and then a projection. So sometimes this really comes from the symplectic geometry and the polarization. But in our situation, actually, we have this complex manifold. We have the Bergman kernel, reproduction kernel, and then the projection. And then we know how to define the Toeplitz operator. We, so to say, we lift the function to L2. There we have the multiplication operator, which is bounded, and then we project down. So it is given by this formula. Do you also see my mouse if I move it?
Yeah, sure, yes.
Okay, very good. So this is the Toeplitz operator with a simple phi. And if you take any subspace or collection of bounded function, then the TA sub A is just the C-star algebra generated by the element in A. Okay, if you have any questions, also let me just know. I'm not sure how fast I am. So what we have been working on, also for example, also with Raul and Matthew, is this question, actually, how can we use group action and representation theory to find commutative C-star algebra, Toeplitz operator, and find the spectrum. So this is kind of the idea in all of this, or this kind of, so to say, multiplicity-free representation, and find some kind of Fourier transform or integral transform that realize the Gelfand transform. Okay, so this was in the wrong direction. So what we are always looking at is a finite dimensional Lie group. You can also look at locally compact topological group, but all the groups that we have been looking at are Lie groups. It acts on a domain. Okay, so just the usual way, also A, B acting on Z is the associative, you act first for B and then by A. The identity acts by the identity. That forces the translation LA to be a diffeomorphism. And we require everything to be analytic, and the inverse is just L sub A. And then it acts on function just by letting it act on the variable inside. And then we know what it means to be invariant. That is, if lambda A of F is always just F, it does not do anything. So that means if you look at the orbit of this map, then you just this constant on it. And if you have some kind of transversal coordinate, then the function is just determined by the value on those transversal coordinate. Those are the picture in the old paper by Raoul and Nikolai and others about the disk. You have the horocycle, the circles, the geodesic, the horocycle, and the circle around 0, and the function that are kind of constant on those, and then determined by the transversal manifolds. And those are very important things in all the construction. In general, we even need more than this, but most in the application, one have some kind of multiplication operator in front, which comes from that the Hilbert space 8 also is given by a measure. So to get it unitary, we have to make sure that we take care of the Jacobian of this action inside of F. So this is usually kind of a square root of the Jacobian of the action, and one has to make it so that it is holomorphic. So in many interesting applications, one actually have to go to a simply connected group, but that will not be a problem. So one of those things that I always stress if we're talking about this is this very simple results that we had in our paper, that this...
Yes, this -1 is misplaced. It should be alpha A minus 1.
Oh, yes, absolutely, actually. Okay, that might be also, yes. I would have to... You mean actually in here in this theorem?
Yeah.
Okay. So this is a index. So yes. the representation, if you put it around, then just by using change of variable.
Yeah, sure.
And okay, that is because my action is so that lambda of A is phi of A inverse.
Mm-hmm.
Therefore, also it is supposed to be inverse in there because, okay, so if you have it here, actually, you have the phi of A is acting on the function here with an inverse. You move it over, and that gives you a phi of A W. Sure. And then that is the lambda of A inverse.
Yes, sure.
Okay, that is just how one... This inverse comes from the fact that you want to have it that lambda of AB is lambda of B followed by lambda of A. Mm-hmm. Okay, so this tells us that the important thing from the invariance, then T, that says that T sub phi pi of A is pi of Ft of phi. So that is just telling us that those two operators, they commute, which is then saying that T of phi is what is called a defining operator. And this is one of the basic objects in representation theory, that is to study a defining operator, in particular when is this algebra of a defining operator abelian for Neumann algebra. Mm-hmm. And what we are now saying is that this Toeplitz operator generated by the invariant symbols, they sit in this for Neumann algebra as a C-star algebra, and therefore, okay, first of all, that this is an intertwining operator if and only if it is invariant. Okay, and if this von Neumann algebra of intertwining operator, which is, as I say, a very well understood object in representation theory, is abelian, then the von Neumann algebra is abelian. Now I see I'm using a different symbol there. This should be T sub L infinity G. Okay? But also if G is compact, which is one of the nicer things in this paper, it is an if and only if statement. So that has allowed us to kind of decide in several cases if we have an abelian algebra or not. And the reason for this is Engel's approximation theorem, and compact allows us to actually take an average as an integral. But this is kind of the main idea. What we are doing is we are looking at those invariant symbols, determine if we have a abelian algebra of intertwining operator. As I say, that is something that is well known. That already tells us we have an abelian algebra, and then find a nice way to calculate the symbols. Okay, so now let us then start with what is the main part, and that is the Fock space. So here it is just a Gaussian measure. Sometimes one actually put a T in there so that one has a family of heat kernel measure, but that is not so important here. And then the Fock space is just the L2 function intersect with the holomorphic function. And this is definitely a measure that is given by a positive function, which is bounded away from zero on compact set. So it's a reproducing kernel, and one sees easily that the reproducing kernel is just given by the exponential function, and one way to see it as an exercise for graduate student always, okay, you calculate the orthonormal basis and then you sum it up and you know what you get is the reproducing kernel, and that is just the exponential function. Okay, and what is important here, so that is exactly this. We know what an orthonormal basis is. This will show up in a calculation later on. Those are just, every holomorphic function is a sum of monomials. Okay, one has to be a little careful here because usually you think of this as a pointwise summation, but now we are talking about the Hilbert space structure, but then one shows this is actually correct also in the Hilbert space. And then you calculate the norm, which is just reduced to one-dimensional case. And that gives us alpha factorial, where I have written down here the definition. And this is an orthonormal basis. That is a well-known fact, at least more than half a century. Okay, now we can write down what the Toeplitz operator is. That is just the multiplication and the integration. One thing that we will actually use here is that if you are doing the inner product, this is also much more general fact, then you are just looking at the L2 inner product. You don't have to kind of use the projection. This is simply because the Toeplitz operator, you think of this, it is the multiplication times the projection. The projection is orthogonal. You can move it over to the G. G is already in the Hilbert space, so it disappears, and you end up just with the L2 inner product. So if you are calculating the inner product, which is actually later on important to calculate the symbols, we only have to deal with the usual L2 inner product. This is a trick that we will use. Okay, so the first group that we want to look at, and this is something that we started actually 1 or 2 years ago. This was the first somehow exercise for Vishwa, was we looked at this product of orthogonal group. So what has already been done is, you look at just a one-dimensional case. That is n is 1, and then just a torus. The references are later. So that is correct. And then if you look at just the product of torus, then because of the product situation in the Fock space, this can also be done. And that was done, I think, in one of the formula in a master thesis of a student of Nikolai. So we are looking at the general case, and one should see also this example includes all of those are just torus, or you can just take k equals to 1, which is just the orthogonal group acting. Okay, and this group acts because we know how the unitary group acts on Cn. So one should always just think of this sitting in the big orthogonal unitary group. So it acts on each of the components. So you kind of decomposes the C into pieces of size Cn. I think Nikolai usually denotes this by psi or something, so I've seen something like that. So you just decompose the space according to this, and then you can also think of, you can decompose then the Fock space also as a product of the Fock space in n1 variable tensor product with something in n2 variable. So you are again in kind of a tensor product situation. One has to be a little careful then also as you start to look at the C-star algebra, because that does not necessarily tell you that the C-star algebra is a tensor product of the individual pieces. But okay, so then it acts on functioning. Here actually one, as I say, one should put a determinant in there in front, would actually force us to go to a covering. But that does not matter in our case for this group. This is, the results do not really matter actually for this factor here. So everything is exactly the same.
So Gesture, basically metaplectic group you need so that you can take square roots.
Exactly.
Yeah, but because you need, for this you need a double covering.
Yes, exactly. That is what it is. This is really actually that the action that comes out if one looks at the metaplectic group. I'm going to talk about that later, then one get this factor, but we decided just to skip it because it is not going to change everything. The symbols, they are anyway still actually just by letting it act on the variable, so that does not change it. This is just a factor, so if you're doing integration of Cn, you can take it out. Mm-hmm. So this is really not going to change really the method or the result and everything else. The Toeplitz operator really are the same because they only depend on the symbol and the projection.
So Gesture,
and the invariance of the symbols do not depend on this because there it is not going to show up. But if one is really exact about thinking of this in terms of a special case of the metaplectic group, then one would have to include this determinant. Mm-hmm. Okay, so I just wanted to point that out because I'm going to talk about that later on. Okay, so for the calculation, then you do the same as I mentioned for the Fock space.
Gesture, wait a minute.
May I ask you a question? So every element in the Fock space can be written as a sum of homogeneous polynomials. So those are the polynomials where the length of the alpha 1 plus blah, 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 the alpha k is equal to n. This is orthonormal basis of that space. What is important for that one is actually that this space is an irreducible space for our group G. It clearly leaves it invariant because the action of the orthogonal group leaves the homogeneity invariant.
Mm-hmm.
And in terms of representation theory, also our action gives us a unitary representation because in the change of variable, you always have the absolute value, the orthogonal group. If you look at the measure, is e to the minus the norm, and the norm does not get changed if you have a unitary matrix. And then what you ask in representation theory, okay, now you have a group acting, and how does it decompose into irreducible? And that is exactly where those polynomials come into the picture. And this is just a factor of that is in almost every textbook, standard example. You look at the homogeneous polynomial and the UN, then that is a unitary representation irreducible of UN. And now you have a product of group, and then the irreducible representation that is given by tensor product. So what we have there is a decomposition of the Fock space into irreducible representation. And what this is telling us is that if you have different m's, then you get different representation. So they always show just one at the piece. And that just tells us, the intertwining operator or each one of those pieces are diagonal. That is the famous Schur's lemma. So that means if you use those coordinates and every intertwining operator is diagonal, they all commute. The Toeplitz operator with invariant symbol is commutative. So this is definitive also gives from this general fact. So now it just is the question actually how to calculate the eigenvalue. Okay, so it is well known that if you have a function that is rotational for UN invariant, then that is a function just of the length. You can just see that because, okay, every element can be rotated then because act transitive of the sphere to the norm times the one of the basic vectors. And it does not depend on that one, it's just the norm, only depends on the norm. And that is the same if you have this decomposition into smaller pieces, that those invariant symbols, they only depend on functions which are bounded and are defined on R plus, and they have K variable. Okay, so you have a isomorphism between those functions. We either write as the function A is A phi, or if you have a symbol A, then the corresponding symbol is phi A. So now we just have to calculate this with the A's. Okay, and here is then the main theorem. And this is, as I mentioned, very much really just the same situation as in the one-dimensional case. So because you have an intertwining operator, then Schur's lemma tells us on every one of those PMs, you have a constant. Okay, which depends on phi, it depends on the dimension, and depends on the degree. Okay, you can kind of think of this as a function from the space X. For me, the natural number always starts with 1. I think I'm not in agreement with Frege, which starts at 1, but in a 0, the cardinality of the empty set, but somehow, for me, it has always been so that the natural number starts with 1, so I have to start with n sub 0. That is kind of a space that we are looking at, that you have taken a Toeplitz operator and mapped it into a function. And you can actually calculate them, the symbol, and that is given by this integral. And to actually save space, okay, your square root is now a vector. That is just a vector where you take each one of the square root of every Lj. The power, now those are indices. This is a vector, R is a vector. But this is just by taking the power of each individual ones. And then we have a factor which depends on, okay, how you decompose the n, that is this one, and how you decompose the degrees. And then you have this integral, which is exactly the same integral as you get in one dimension, except now everything is just one dimension. But you have to do it in all of the dimension, all of those factors. But the formula is pretty much exactly the same, and that will be used in a moment. Okay, so this is, I think it is, I'm not quite sure if it was only Nikolai. I thought certainly it is not, they were co-author, but so this is the formula what you get in one dimension, and this is the same formula, except also I have the feeling there might be a typo here, that it was m factorial. There's a missing 1 here, because we have the n here, so I think there's a missing 1. But the formula is exactly the same. So in particular, let me just put them all up. Okay, so this is the one-dimensional. If you now do the full group, which actually is what we started with, then you get this formula. Now you just have one decomposition. Okay, so k is equals to 1. And what is interesting here is that what you get is, this is the same formula. Okay, for the un, invariant symbol depends on a function defined on L plus. And this function actually defines an invariant symbol in every dimension. Okay, not only in one dimension. You can actually, for every dimension, you can put the norm offset in there, so it gives us a un invariant symbol. So you have the map from L2, the L infinity, L plus, into all of those invariant symbols. And the nice thing is that the only thing that happens is, on the left-hand side, you have the dimension, but on the right-hand side, you have just the one dimension, but because of the shift here in the integral, you are just shifting the m. So you can think of this kind of going from one dimension to another. You are just taking the same set of eigenvalue, correspond to A, but you shift it, which I think is a very, very nice formula. And this is actually a continuous map in the right topology. And the other thing is that if you actually now have a product situation, actually then the symbols are just product, because in this general formula in here, so you would have the product everywhere. You take that just individually, so the symbol is just a product. So in that sense, actually all of those products sit inside there. So those are the simple consequences of the general formula. But also, how is the proof? I am just somehow the idea. I do not know how well those formula. This is just the polar coordinates. And you can use this to actually calculate now what happens if you have a homogeneous polynomial. Then polynomial is completely determined by the restriction on the sphere. and you want to calculate those two norms. Because in the integral, what you get, actually you use the polar coordinate, you can take the R out because that only depends on the degree. And then you have an integral over the sphere, and this is the formula. And now we see also, aha, here it is where you get the gamma factor, okay? So in particular, we have a formula for the norm of the orthonormal basis on L2 on the sphere. And now the thing is really just very simple. You want to calculate the eigenvalue. Okay, that is, you just take then actually one vector in that space because you know a priori that your operator is diagonal. So you just have to let it act on one vector. You get the multiple of that vector, you take the inner product, and out comes the eigenvalue. Where we are now using that the vector is a unit vector, okay? And now I have actually changed the notation. That is because I was in a hurry writing this down, and I'm taking the notation from the old paper. You calculate the norm of those polynomials in each of those dimensions. You get a gamma factor out there, okay? And then you just do the calculation. So the calculation is extremely short. You just have to set everything up so that you can use it. And okay, you use by actually first by decomposing the Cn, and that is a product situation, and you have the symbols. Okay, now on each of the coordinates, you do the polar coordinates, so you get the Rj. Now we have to remember we are in a different dimension, so we get the 2mj and -1 on each piece, that is the polar coordinates. The exponential function is nice. Out here, because you have homogeneous polynomial, you get one more factor of the LTAs, and then the norm of the QJs on the sphere. This is the only piece that depends on the integral on the spheres. But we just calculated what this is. And then we do the calculation, and just as in the one-dimensional case, we do the change of variable by putting the square root in there, and we get the formula. Okay, so after setting everything up, the calculation is not that bad at all. The only really things that one needs here is this formula here. This is a very well-known actually formula for the Fock space and sphere, or shows up in the beautiful book by Faro and Korani on von Neumann algebra, on tube-type algebra and Jordan algebra. Okay, so what we next do, actually after having this, we have this space. That is where our symbol lives as a function. You put on that the metric, which is just the sum of those square root metrics that shows up in the one-dimensional case. You look at the uniformly continuous and bounded function. It's a nice C-star algebra. And then you can also writing it by using oscillation. It's also quite common to call those functions slowly oscillating function. And that is what we write here actually. It is a slowly oscillating. And then what you get is, okay, the symbols are, okay, there is a typo here. Exactly the function on this higher dimensional space, which are slowly oscillating, and that is, okay, this was the paper that I was thinking of, sorry, so it was not Nikolai. So you get the same results really in the higher dimension and in the lower dimension. What we have been thinking about, and we are tending towards saying 9, no, that, okay, so this space of continuous function, the C-star algebra, is not the tensor product of the function of lower degree. This is bigger, okay? So one has to be a little, as you move over to the C-star algebra, if you have a product of symbols, you get the product of the eigenvalues, so kind of you get the tensor product in there, but it looks like actually this space of continuous function actually is bigger. But I have to admit, I do not know the answer. And I have also been thinking of what is actually, we know that this corresponds to compactification of N0K. What is this compactification? I don't know. And I think it is maybe not the right question to be thinking of. So, but it would be good. Someone in logic would probably want to know that. So this is one of our main theorems. But let me actually say a few words about then what we are going on, also doing, what our more general project is. So what we know is you have this Berezin transform that goes
Sorry, it's Bargman transform.
Yeah, it's okay. I grew up, okay, so the Berezin transform we usually a different, okay, Bargman transform, let's do that, okay, Bargman transform. So what that is, so this is just an integral transform. You have the B star, so those are unitary isomorphisms. And what is very easy to do, kind of, that quite often we have group acting on L2 on a way that we can easily know or easily describe. We can transform that to an action on the Fock space. Mm-hmm. Or in the other way, if you have something like the action of the UN on the Fock space, which is obvious, then we can transform that to an action on L2 of L, where also how on earth does a unitary group act? So in representation theory, one jumps up and down between those two realizations, okay? So the groups that show up here is actually a big group. So first of all, what one has is the Heisenberg group and the Schrödinger representation, which is extremely important in time frequency analysis, the windowed Fourier transform and other things, and also a representation theorem. This is probably one of the most studied representation. This acts by translation on L2, but also by modulation. Okay, so if you switch the coordinate, you get actually almost the same thing. And then it is the central factor, and it's well known that this is an irreducible representation. You could put in a parameter lambda in here, and then it is uniquely determined kind of by the action of that parameter. So this is one thing. So what we have then in here is translation. We can carry that over and get what Nikolai calls the horizontal symbol. The Berezin transform, it defines it. You get L2 of L, that is via the Fourier transform, and multiplicity 1, representation, decomposition. Every operator there is therefore diagonalizable, so that is definitely a commutative algebra of C-star operator, C-star algebra of Toeplitz operator, and the symbol can be calculated via the Fourier transform. And that is what Nikolai did, except also he did not look at, he looked at I times L, if I remember right. Okay, so that is one way. And this is the actual kind of what one, I have the feeling there is a factor missing there. Okay. So that is one thing that one can do. And then it is the metaplectic group. That is kind of, one looks at the automorphism of the Heisenberg group, which includes the symplectic group. That leaves the center invariant, so it leaves the commutes with Schrödinger representation, and then gives us a big group of not matrices, because it is a double covering of the symplectic group. Okay, and what we are looking at is all of those groups that you can think of here. This is what we looked at in the paper with Vishwa. Those are the horizontal one. They all lives in this product of the metaplectic and Rn, and you can let that act. Again, actually, what gets the same, actually, you have the symbols become a product kind of, results is the same. Or you can go to other groups, and one thinks of the symplectic group, as to say for the determinant, one has to take a square root and go to a double covering, and that is then the metaplectic group, except now the representation is much more complicated. It is given by an integral operator. But this is from the book by Folland. This is well known. So one can start playing with it. And what we are actually now looking at is the group of rotation, now real rotation, and then dilation. And one of the reasons that we want to understand this is now there is not this representation by a factor in front. We are looking at this simple integral operator because, okay, there is no problem with the orthogonal group that preserves the norm, but one would get a dilation in here. So those groups are lying in here on the diagonal. Everything on the diagonal, this is 0 and 0. So everything that comes in here with the B, that is 0. So the only thing that is interested in this factor here. So this is really just the dilation of the reproducing kernel. That is all what comes in there. And this is actually the invariant symbol. They give a commutative C-star algebra. But we have not calculated the symbol or kind of determined the C-star algebra. That is still a work in process. And then here is just a list of paper dealing with the Fock spaces. This is far away from a complete list. There is a very nice book by Wallach also, but I could not find the exact reference, so I skipped that. So there are a lot of reference to the Fock space. It is very interesting space for representation theory, physics, Toeplitz operator, complex analysis, and other things. So I think I will just stop here if there are any questions.
Yeah, sure. Please, any questions? Who have a question? Gestor, may I ask you a question?
Sure.
Yeah, you know, this metaplectic group is always something mysterious because it's
Yes.
not matrix group.
Yes.
Can you give a kind human understandable description of that?
Okay, so what you are doing is actually that, okay, you look at this representation here with maybe a lambda factor in here, okay? Then you look at all the automorphism of the Heisenberg group, okay? So if you have an automorphism and a representation, you can conjugate the representation, you get a new one. But because it leaves the center invariant, then what you get is the same factor lambda in here. That means that you get the same representation, so you have an operator on the Hilbert space L2 that commutes, or it's an intertwining operator, okay? So every operator in the representation, or in this automorphic group, is associated to an operator of L2. Now, because what you're doing, you are conjugating the representation, then it actually gives you that you get a representation of the semi-direct product of the automorphic group and the Heisenberg group. Then what we know is the Heisenberg group is given by a multiplication in the x and the y. You get just the addition. On the center, you get a t plus 1/2 of the symplectic form of x and y. Usually just written by x plus iy, that's a complex number, so it's just the imaginary part of that complex number. Multiply together if you have two of them. Okay, and then you see the symplectic group is then one of the automorphisms in there. The symplectic group leaves this inner product as the symplectic factor invariant, so that is an automorphism of the Heisenberg group and hence of the Schrödinger representation. So for every element in the symplectic group, you actually get an operator. But now this operator, okay, if you multiply two elements of the symplectic group, you don't necessarily get the product of the operator. You get the product up to a factor of in the torus. So you would have to lift, this is what we call a projective representation. Mm-hmm. And then you show actually you only have to go to a double cover. Mm-hmm. So that is somehow what this double factor cover comes from the unitary group. Okay? Because if you look at the other ones, so that is everything can be looked at simply connected. The only product with the covering is this torus in the symplectic group. So a priori, you would have to take an infinite covering, but then you show it actually is only a double covering. Okay, so that is kind of what I usually just think of. Where did I start it? In most cases, you can kind of be happy by looking at the symplectic group, or group of this form here. And that is also what are interesting are all the linear group here is sitting in here. So you can look at all groups element in here. That will be diagonal group and other you can produce a lot of examples there. Or you can put a subgroup of the unitary group on the diagonal. Okay, so this is all part of the metaplectic group. And as I say, if you want to really follow that exactly, you would have to put the square root factor there in the front. Mm-hmm. But it does not change our results, it just makes it a little more complicated. Another group which is interesting, that is if you put in a symmetric matrix here. This is and one on the diagonal. This is a group, for example, the symplectic group is very important as soon as start to look at tube-type domain and holomorphic functional Bergman spaces on the tube-type domain. Then this group with the symmetric matrices here is a very important one that you can use. And you can look then also at invariant symbol, and that is a multiplicity, one decomposition, and a commutative algebra. So what I'm saying kind of, as soon as one steps into the Metaplectic group and the Heisenberg group, one can start to produce a lot of other examples which are not so obvious if one just sticks with the usual thing, in particular this one here. The rotation and the dilation. And I think this is actually a very nice example. This is a group that shows up in tomography and a lot of other things. This is kind of the natural group. If you are looking at the Beresing transform, you know that this group acts on by dilation and rotation. So kind of what it is all determined by is what this is doing on the sphere. Okay, and then you are doing simply spherical analysis. Harmonic function, harmonic polynomial. So those harmonic polynomial, they come in as soon as you start to look at the symbol.
So basically, if you do spherical coordinate in Rn, it will be just a group like a tensor product of one part acting on radial direction, another part this SON on spheres.
Exactly. Exactly. So that is why I kind of like this example. This is a little more complicated than the other example, but I thought this was a nice example to kind of try out those ideas.
It's then via Bargman transform, you would like to bring this to the Fock space.
Yes. I was actually hoping that one could actually come up with a new integral transform that made it simpler, but I have not come up with that. But the Bargman transform definitely works, and then you transform the Toeplitz operator to operator L2. You use the polar coordinates, and that should actually then gives you a integral over the radial component and the spherical harmonics. That is some of the idea, but we have not done that in detail. So we are also happy kind of wondering about other examples, but decided to concentrate on this one because again, you get nice thing in there, so the analysis on the sphere and spherical harmonic. Those are always very nice things.
Okay.
So this is what we are working on. We are also kind of trying to write down, I actually, do you still see it?
Well, we are seeing you right now.
Oh, okay. So I probably canceled the...
No, you know, it's much better than to see your slides.
Yes.
To see you in person.
Okay, you do not quite see me in a person, but then actually what we are also, we have kind of written out the short proof actually if you have those dilation, translation in some coordinates and rotation in other coordinates, that you kind of get this tensor product situation again.
Okay, more question, please. Raul, any question?
Maybe something about the references. You mentioned a book by Balak. Is this the one?
Oh, yes, absolutely. This is, I only have somewhere a digital version of this. This is a very nice book. I like this book much better as Fock, actually.
Raul, show it again, this book. Just you'll see. Symplectic geometry and who is Wallach?
Fourier analysis.
Wallach. Yeah. Wallach is the same like Wallach set?
Yes.
Okay.
And this is the second edition.
Yes. I did not know that this was available as this is the Dover book?
Yeah, the Dover book. I just bought
The only thing that I don't like that is, this was at the old days, I think people had to type things up. So
Raul, can you send us email with the title of this book, exact reference?
Yes. I don't know if you can, I bought it in Amazon. I think you cannot download it, but well, it's available in Amazon.
Well, any case, please send the reference.
Yeah. This is actually the book that I learned it from as a student, actually. As I was interested in this, also that from the point of view of symplectic geometry and Fourier analysis operators.
Great. More questions, please?
I have some questions, Egor Maximenko.
Yeah.
Well, one simple question. Did you think about generalizations of these results to other spaces, for example, harmonic spaces or pluriharmonic spaces instead of analytic?
I have, as I say, actually my original motivation that I was actually working on the 96 or something, that was more general symplectic manifold. But then I never published anything about it, but I have thought about it, but I have not written anything down, okay? So I would love to actually have, probably if I had a graduate student or postdoc or whatever, to discuss that. What I am kind of working on with a graduate student now somehow is, there is a very nice paper series of paper by Engels and co-author and about analytic continuation of Toeplitz operators. So we are now looking at what happened exactly, what Nikolai wrote down, the Wallach set. But I am aware of some of the paper, but general situation, but my answer is no, I have not done anything there. My explanation would be, if one has a nice groups working on those bases, things should work. Okay, this is probably way too general statement, but the group theory kind of, that is why I like it. It is kind of a black box. You have it, you put it in there, it tells you what you have to do. It is a recipe kind of. Okay. But I will be open for all discussion about other situations. I think this leaves out as a lot of direction where one could go. So if you can point out to me nice references, what you're thinking about or what one can do, happy to discuss it.
Well, if you don't want to do it, there are other experts who will do it.
Please go ahead. Please go ahead. As I say, I have now 2 students working on Toeplitz operator. That is Vishwa, and then there is another one, and he is looking more on paper what pseudo-convex domain and what this paper by Engels and co-authors.
Oh.
Igor, more question?
Yes, please. I have one naive bibliographic question about Weyl operators. Weyl operators, weighted shift operators in the Fock space. They do not form a true unitary representation. They form a projective representation. Could you please recommend a book or a paper that explains why they can't form a true representation?
Oh, this is a very, very good question. I mean, you probably know the book by Fock. I think he discussed this, but
you mean harmonic analysis on the
phase spaces?
Phase space.
Yes.
Folland, yes.
Yes. But this is a very actually old question. Actually, this already started by Mackey, or actually probably already by von Neumann. That was exactly this. You have kind of a representation of the group. Okay, so the history then I'm trying to build up where one can find it. You start with also quantum physics, also what you are actually acting on is an operator on the projective space of the Hilbert space. Okay, because you are looking at unit vector, which are also just element in the projective space, and then you ask the question actually, can you lift those operator up to the full space? And what you get there is you can do it modulo a factor of length 1. And this is the cosine. And this led Mackey to study projective representation. And now you ask yourself, can you actually get rid of this factor?
Yes,
One
exactly.
way to,
yeah.
Yes, and there is actually a paper by Mackey. There's also a very nice by Varadarayan. He always writes very nicely. I'm just trying to figure out what the references is. I actually wrote, one of the things that I do is work on those Bergman spaces and then sampling or discretization of those. And I have a paper with Jens Christiansen. In that paper, we have the reference actually for those questions about the projective representation. So I don't remember exactly what paper by Varadarayan it is, but that is kind of my standard reference. And it is always a question about cohomology group, because what you have is those factors, they satisfy certain co-cycle relation. And there is also a notion of being equivalent. That is, if you have kind of just multiplication operator, so you have an equivalence relation, you have a boundary value or map. So you have everything that you need for cohomology. And then the question reduced down to, is it trivial or not? And in those cases, for example, with metaplectic group, so if you just think of this as the symplectic group, the answer is no, it is not trivial. And then you have to go to a double covering or higher covering. Sometimes you have to go to infinite covering. Or you can actually use what is called the Mackey group. That is, you take this group of operator or group that you're looking at, and you extend it by the torus using this cosine. And then you have a representation of that group. A typical example is exactly if you look at translation and modulation of the group M2. If you flip them, you get the exponential factor.
Yeah.
This is the fact that you actually have a projective group or projective representation of R2N. Mm-hmm. If you do the Mackey extension, you get the Heisenberg. Mm-hmm. And this is a trick, actually. The only thing that one tries to avoid this is you might end up with a terrible topology.
Terrible what?
The topology on this new book is
okay.
not necessarily the prototype. It depends on the analytic property of the co-cycler. So one has to be a little careful there. But I can look for references and just email that to you.
Thank you very much.
I think I have your email address.
I will repeat my question by email.
Yeah,
I will send you an email.
Yeah. Yes. And I remember also after we met in Mexico, I actually had a question to you, but now I've forgotten it. I'm getting too old memory for it. Okay.
Okay, more questions?
I have one question more. One more question. Could you please show us the page 21 or something like this?
Okay. So let me then share this again.
Where you introduce the square root matrix and something like this.
Do you see it now?
Yeah.
Okay, so let me put this into a full screen here.
It's okay now.
Okay, so which one was it?
Something about 21.
Square root matrix.
Yeah. And the theorem. The theorem, the next, I didn't understand how to prove the surjective property of this mapping.
Okay, have you looked at the one-dimensional case?
Well, we did the one-dimensional case with Kevin, yeah.
Yes, and what we kind of did, we kind of just reproduced the idea there. I agree also, I think this is really the length of the paper. Then I can actually, if it is okay with you, we have a preprint which is not at all complete. If you promise actually not to distribute.
No, just I had curiosity about the main idea. So,
yes, the main idea is really, I mean, what you can think of is, you see, I'm not going to say that the tensor product is enough, but you can see you get a lot of it. The problem is also the continuous function are not necessarily the tensor product. Okay, this is algebra. So you would have to repeat everything that you did in the one dimension, but an analysis is not very much more complicated, okay, because the integrals are exactly the same, okay?
I see.
So let me just, because those are several page calculations, and therefore I did not want to do it, but we really studied the one-dimensional case very carefully, what you did, and then we reproduced that, so to say, for the other case. And for UN kind of, I mean, that is obviously clear because this is just a translation. Then we proved actually that this translation is a continuous map. That was one of the steps, so we used that. So that definitely gives you, whatever the dimension is, that all of those products are in there.
Yeah.
And then you have to do actually a little more extra where you do not have a product. And I think actually let me just see. If it would have been enough just to study the product, would that not just lead to that the C-star algebra is the C-star algebra tensor product of its individual pieces? That is my feeling. This was somehow our first idea, kind of actually, what was my idea, but I think Vishwa corrected me. That is not enough.
You know, Gester, there is general fact. If you have sister algebras that are isomorphic to C on some compact, and you tensor such algebras, then you have algebra of continuous function on the direct product of these compacts.
Yes, but now you have to be careful. This would be correct if you knew actually space, the compactification.
But you will never know it because it requires nets and everything like that.
This is exactly the point. So we looked at this, and that was the idea that we had, okay, it is a tensor product situation, but now the space that we are looking at is not compact. So you are looking at functions which are uniformly continuous and bounded.
Yeah.
What can you say now if you are looking at a tensor product? But I agree also, this was exactly the reason that I thought we are in a tensor product situation. But then there is I don't know exactly where Vishwa found it, but there is a counter example actually if you take non-compact spaces. So she found this counter example, and that kind of changed our discussion. But I still think it is nice if one, you say you will never find it. I don't know. I thought this was maybe completely waste of time. I could have done something.
It's a kind of stone check compactification in that sense.
Yeah, but I don't think this is the full.
No, of course not full. Of course not full.
Exactly.
Yeah.
Yes. Exactly, that is. It still actually is an interesting question, actually, kind of, we have not got into that, is to describe all the homomorphism on this algebra.
No.
What if there is kind of a nice description?
Well, you may approach it point of this compacts by some net.
Yes. Exactly.
This is only what I can say.
Yes, I know that this is what you did with your master student.
I don't know. I don't remember.
I saw something else. I thought it was a master student. He was looking at a different situation, but there was this also discussion about those nets, but I did not quite so far understand that. So. So, yes, so that was something that we talked about, but never really worked out. So, you know, also in 1 year, Vishwa will be looking for a postdoc position, so.
No.
You can.
Well, with this coronavirus, nobody knows.
No one knows that, correct.
Yeah,
but I am hoping that at least next fall, actually, one can start to.
Yeah, one can start reasonable activity.
But I have to admit, actually, I really hope that one thing will survive it. That is kind of once in a while having those Zoom internet.
Yeah, online seminars. Yeah, it definitely is a good thing. Yeah.
Very nice idea, so that one can now hear people from that otherwise would be impossible to. Yeah. So I think that is very, very nice.
Okay.
Only problem with that is you don't have time to listen to all of those talk you would like to hear.
Yeah. Thank you very much, Gestor. It was a very nice talk. We are very glad that you did it in our seminar.
Thank you for the invitation.
Yeah. Okay, so just for participants of the seminar, now we have a break till March 2. Mohammed, are you here?
Yes.
So next March 2 and next 2-year talks.
Yes. I gave the title and abstract to Maribel.
Yeah, definitely. Thank you very much.
So my first talk is March 9, right? February 9, right?
No. Your first talk, March 2.
Okay. And the second one, March 9. Okay.
The second one, March 9. Yeah, sure.
Okay.
So best wishes to all and take care, especially with this coronavirus.
Okay.
Thank you very much for all.
Hope to see you sometimes in person.
Yeah, definitely.
Okay, bye.
Bye, 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 bye. Bye to all. Thank you.
Thank you all.
Bye.
Adiós. Nos vemos el próximo mes.
Nos vemos el próximo
luego.
mes. Raúl, por favor, nos mandas el título.
Sí, bueno, sobre eso te pregunto, creo que varios recibimos un email de una lista del seminario.
Ah, lo que pasa es que yo mandaba 2 correos separados, uno para la lista Berman que teníamos ya originalmente en nuestro seminario y uno para todos los que se incluyeron este semestre. Pero lo que hice fue meter a todos en la lista Berman y para solamente enviar un email.
Creí que sería alguna lista de discusión, pero
No.
para poderla aprovechar, pero bueno, no directamente se los puedo mandar a varios de ustedes, la referencia.
Otra cosa que quería mencionar, mañana debe de ser un coloquio de la UNAM, plática de Carlos Villegas. Algo puede ser interesante para todos. No me recuerdo el título, pero se trata algo sobre geometría simpléctica, cuantización, algo en este estilo. Es a las 11 mañana.
¿Y cómo entra uno ahí?
Como es,
Yo tengo clase.
mandaron correo electrónico de la UNAM